Hey guys, Mr. Backerberg here. In this video, we're going to take a look at indefinite integrals. So as we're talking about indefinite integrals, the family of all antiderivatives of a function f of x is the indefinite integral of f with respect to x and is denoted by this integral symbol, f of x dx. So if capital F is any function such that capital F prime of x is equal to f of x, then the integral of f of x dx is going to equal that capital F of x plus c, where c is some arbitrary constant, which is called the constant of integration. Now, an indefinite integral is different than a definite integral, even though they look kind of similar. A definite integral is a number which represented a limit of a sequence of Riemann sums, or we looked at it as the area underneath a curve between the curve and the x-axis, whereas an indefinite integral is a family of functions that all have a common derivative. Now, just like we had properties of definite integrals, we also have properties of indefinite integrals, and they're very similar. So if we're doing an indefinite integral of k times some f of x function dx, then what we're allowed to do is pull that k constant multiplier to the front of our integral, so then it would be k times the integral of f of x dx. And then another property that we've sort of seen before, if we're doing the integral of two functions being added or subtracted together with respect to the same variable, then we're allowed to split up those integrals, and in this case do the integral of f of x dx plus or minus the integral of g of x dx. Now we're going to run through a list of common indefinite integrals, and the first things that you might see are some things called power formulas. So this first one says if we're doing the integral of x being raised to some nth power dx, then what we're going to do is take that x value, we're going to add 1 to the power that was there initially, but then we're going to divide by the power plus 1. And then we have to add that plus c on the end anytime we're doing an indefinite integral. Now, this rule only works when your n value is not -1, because if your n value was -1, then you'd get 0 on the bottom of this fraction, and you're never allowed to have 0 on the bottom of a fraction. So this is like our anti-power rule if we think about doing the opposite of a derivative. Now, let's say that n value was -1, so then we'd be looking at the integral of x to the negative first power dx, but we could also write that, since we don't usually like negative powers, we could write that as the integral of 1 over x dx, and when we're evaluating either one of those types of integrals, that's going to turn into the natural log of the absolute value of x, again with that plus c on the back end. We always have to include the plus c when we're doing indefinite integrals. Next set of formulas we've got are some trigonometric formulas. So if we're doing the integral of the cosine of x dx, that's going to integrate into the sine of x plus c. If we're doing the integral of the sine of x dx, that's going to integrate into negative cosine of x plus c. If we're looking at the integral of the secant squared of x dx, that's going to turn into the tangent of x plus c. If we're looking at the integral of the cosecant squared of x dx, that's going to turn into negative cotangent of x plus c. If you've got the integral of the secant of x times the tangent of x dx, then that's going to turn into the secant of x plus c. And if you've got the integral of the cosecant of x times the cotangent of x dx, then that's going to turn into negative cosecant of x plus c. Again, notice we always have to put the plus c on the back end when we're doing those indefinite integrals. And then our last set of formulas are some exponential and logarithmic formulas. So if we're doing the integral of e to the x dx, then that's going to stay as just e to the x, but we have to put that plus c on the back end. Now, if we're doing the integral of some number a being raised to the xth power dx, then what we're going to do is take a to the x and divide it by the natural log of a, and again put that plus c on the end. If we're doing the integral of the natural log of x dx, then that's going to turn into x times the natural log of x minus x plus c. And if we're doing the integral of log base a of x dx, now this could also be rewritten using a change of base formula to say the integral of the natural log of x divided by the natural log of a dx, then what that's going to be is x times the natural log of x minus x all over the natural log of a plus c. So in this example, we're going to look to see if we can use some of those indefinite integral formulas to help us evaluate this indefinite integral, where it's the integral of x squared minus the sine of x dx. Now the first thing I notice is that there is subtraction happening in here. So what we're actually going to be allowed to do is evaluate each one of these integrals separately. So we're going to have the integral of x squared dx minus the integral of the sine of x dx. Now this first one is x being raised to some numerical power, and that number power is not -1. So we'll be able to use our anti-power rule here. So what we're going to do is take x, we're going to add 1 to the power, but then we have to divide by that same number. So the integral of x squared dx turns into x cubed over 3. Then we've got minus subtraction happening in here. Now the integral of sine of x dx turns into negative cosine of x. But then because we just did an indefinite integral, we always have to put our plus c on the back end. Now I notice that in the middle right here we have a minus a negative, so we can take that minus a negative and turn that into addition. So then we're going to say that our final answer for the indefinite integral is x cubed over 3 plus the cosine of x plus that c value. That's going to be it for this video. Thanks for watching.